Okay, let's get started. So, are there any questions since last time? Yeah.
I'm doing, but like, I was a little confused when S had like states where like double S's within itself.
Yeah.
So we still have to make the initial like new start state going to S.
Yeah. Mm-hmm.
Right. Okay. Yeah, I was confused when it's like two S's within itself.
Yeah. So remember, a rule always is you take the variable on the left side and you replace it with the thing on the right side, whatever it is. So if it could be the same variable or multiple occurrences of it or just anything. It could be anything. So you're just replacing the variable with the thing on the right-hand side. That's all that we're doing. Any other questions? So I'll have quiz 10 graded by Friday. I didn't get a chance to get that one. I'd rather get your homework done first. Yeah.
For the homework that's due Friday, the third question, do we have to, you say explain, do we have to like prove it or?
Well, you'd have to give some kind of convincing argument as to why it is true, because I could just say, oh, here's how to show it's context free, or here's a method to show that it's not context free, and I could just claim that it's true, but then that doesn't actually show that it's true. So you would have to explain it as to why that it is true, whatever method you choose. Yeah.
There's a way to do it without using like PDAs.
Yeah. The PDA way is a lot easier, but with CFGs it is possible. Because we haven't talked about it yet. But yeah. Any other questions about the homework or anything else? Okay, so what did we start talking about last time? Yeah, the conversion of a grammar into CNF. Yep. So Chomsky normal form. Believe it or not, there's another CNF in what I do for research. So I almost said the other one, but it's Chomsky normal form here. So I have to always think that. Okay, so if we're converting into CNF, can anyone remind us what CNF means? So what does CNF mean?
That means that the start state must go to empty string, that a variable can either go to a terminal or two other variables.
That's almost right. And we can have a terminal. So there are some things that we need to be sure of. Do I have to have the start variable going to empty? No, it's just that the only possibility of having empty on the right-hand side is with the start variable. I can't have anything else on the left side than the start variable. What about the two variables on the right-hand side of that middle rule? Right, they can't be the start variable. Good. So there's no way, once you apply a rule with the start variable, there's no way to go back to it. Okay, cool. So when we did 2 steps last time in the 5 steps it will take to convert this into CNF, one thing that I should note is that how many of you are reading the Sipser textbook? Okay, so for those of you who are, you'll see 4 steps in the conversion, and then you see Ryan saying that there are 5 steps. So there's it turns out that Sipser combines the last 2 steps into one. So I prefer to have them separate because it's easier to understand. But either way, what are the first 2 steps that we did last time in the conversion? Yeah.
The first one was to ensure that we don't have the start variable on the right-hand side. So
Yeah.
we made like a new S0 and that went
Right. So just ensure the start variable is not on the right-hand side. Cool. What was the second one?
It was to eliminate the epsilon.
Yeah. And I put this in quotes because we're not literally eliminating them, but rather that we're simulating these epsilon rules with other rules and then eliminating them. And then the third step we did, and I copied the grammar here so we can start working from it again, where we're eliminating unit rules. So what's a unit rule?
It's one that goes from variable to variable.
Yeah, so one variable to another. And we had several examples of that. And what we did was we copied rules around from one place to another to simulate the unit rule. So we had S0 goes to S, and so what we did was we copied the rules of S up to S0 so that we don't have the unit rule anymore. Okay, so is this grammar right here in CNF? No, so what's an offender here? Any example?
All of the variable, like anything with a variable, it should just be two variables as opposed to we have variable terminal.
Yeah, we actually have a lot of culprits here. So we have, like, say this one is a culprit. So, well, our goal is to have two variables on the right-hand side instead of more. Yeah.
Do we need the second rule? Because S goes to anything but nothing goes to S.
Good point. So this rule is completely unused. So S goes to B will be completely unused because we can never get to S in the first place. So you're correct in the sense that we could eliminate that rule and the grammar will be unchanged in terms of what it can generate. I'm going to leave it in because I want this process to be completely algorithmic so that we can apply this to any context-free grammar and not have to think about, should I eliminate this rule or not? So I'm going to leave it in. It's kind of like the regex to NFA construction where we had, like, say 0, 1. And what I said to do was to put the 0 for NFA, the 1 NFA here, and an epsilon transition between them. It's not strictly necessary, but I want this to work in every case. Okay, but you're right, we could remove it. Okay, so the goal, of course, is to have two variables on the right-hand side and nothing else. Well, we have some rules that have more stuff. So let's try, instead of jumping the gun and going to two variables automatically, let's try to bridge the gap, so to speak. Start with this grammar, get to a stepping stone, and then from there, do another step into getting something in CNF. So the fourth step is to ensure the right-hand side is either a single terminal, which is in CNF, of course, or only variables. Okay, so I'm going to copy the grammar down. Here we go. So let's actually look at some rules, for example. So let's look at this S0 goes to B rule right here. So is that rule in accordance with CNF? Variable goes to terminal. Yep, so that one's fine. And in fact, all the ones that go to a single terminal are perfectly fine. And all the others happen to not be. So let's actually look at, say, this rule right here. S0 goes to variable A, little terminal A, and variable B. So the goal of this step is to have only variables here. So what could we do? Well, we have two variables, but we got that pesky terminal in the middle. So what could we do about that? Well, let's see. if I put some variable in here, let's just call it x sub a, and I had so that's a new variable where xa only makes the terminal a and nothing else. Would that accomplish what we wanted to do with that rule? Yeah, because, well, the right-hand side is only variables of the top rule, and x sub a is the only thing it could generate is the terminal a, which is going to do exactly what we wanted to do in the first place. So for the other rule for S0 goes to terminal a variable b. What should we do with that one?
Convert it to x.
Exactly, yeah. So convert this guy to xa. And in fact, every other occurrence of that terminal a, we can substitute in x sub a. Because it just happens that there's so many rules that are very similar. Okay, so all we're really doing is we're substituting a terminal for a corresponding variable that only makes that one terminal and nothing else. What about those b's in the middle? So should I make an x sub b and go to b on those? No, why not?
Because single terminals are done.
Well, single terminals are done, but let's just suppose for the sake of argument that I did do this, where I made an x sub b going to b, and I'm going to replace the b's with the variable x sub b.
Well, what I was saying is it's not done. It's fine because if we did that, then it's not going to be in CNF because we need to have two variables.
Right. What did I just introduce? What?
An illegal rule.
Well, yeah, but there's a specific name for it.
Unit.
Unit rule, right. Because I have exactly one variable on the right-hand side. So the order of these steps is so that I don't reintroduce problems that we've already fixed in earlier steps. So here, I'm not going to replace that b. But I will replace the a's like we did before because there are two either variables or terminals on the right-hand side for those ones. If there's only one either terminal or variable, well, there can't be one variable because we've already fixed those. But if there are two terminals or variables, you convert the terminals to variables like this. Okay, any questions about this one? Cool. So is this thing in CNF? No. So what are the problems with it? Yeah. So we've made some progress. So like the last two rules of each line are okay because they have one terminal or two variables. So that's good. What about the ones that have three variables? Well, we don't have two variables there, so we are going to have to do another step. So the fifth and final step, and one of the easiest ones, is to quote-unquote eliminate long right-hand sides. So I'm going to copy down our grammar again. Paste. There. Let's move this guy down a bit. Okay, so what can we do here? Yeah.
Could we make like a new rule called like C where it goes to x a b and then instead of going a x a b we go a c, something like that?
Yeah, how about that? So let's try that. So could I say I'm gonna remove the XAB right here. I'm going to replace that with a C, which is a new variable. I'm gonna call it C1 for this because we're gonna have multiple of them. I'm gonna call it C1, and I'm gonna have C1 only go to XAB. I think that's what it was, yeah. So, does this work?
Mostly.
Mostly. Well, let's see. If I applied that rule that we just modified, well, we have to go with A, so that's the same as the rule that it was before. Then we have to choose C1 because it's in the rule. Well, C1 only goes to those two variables. And so therefore, we would have to, in sense, apply the exact same rule that we would have applied before. So we're just simulating the long right-hand side with multiple shorter ones. Okay, what about the other XABs down there? I think I can replace those with C1 also. And that's exactly what I'm going to do. To be perfectly honest, for correctness purposes, you should make a new variable every single time. But if you just have XAB as the right-hand side and you just replace it everywhere with C1, it doesn't matter because it's a context-free grammar. But for correctness purposes, you should make a new variable every time. But I won't require you to. Okay. What about that? The other. Oh, so we have one more right here. I gotta fix that. C1. So I replaced all of the XABs with C1. Are we in C and F yet? No. Oh, what's left? Yeah, that bottom left one. So, well, I don't have either BXA somewhere or BB somewhere. So, what am I going to do? Yeah, make another variable in a rule. Good. So let's make a C2 that goes to, which one do you want? Do you want BB or BXA? BB is fine. So I'm going to have C2 go to BB. And then in the rule above, I'm going to replace BB with C2. Yeah.
If on the right-hand side we had like 4 variables, would we do 2? Yeah, 2 things.
Right. So this is a good question. So if you have more stuff on the right-hand side, so let's just say we have A goes to B, C, D, E as an example. Then what you would do is you would have so there are several ways that you can approach this. So you can say, I'm going to have X1E, then X1 goes to X2D, and X2 goes to BC. I think that's right. Yeah. So what you would be doing here is you're making a chain of rules here. So here, X1 would be the next thing in the chain, and you have E on the end. Then X1 gets the 3 variables in the middle, which will now get the D at the very end, and then X2 will get the 2 variables at the beginning. So you're chopping off one variable at a time until you reach the front. Another way you can do it is to do A goes to X1, X2, where X1 makes BC and X2 makes DE. Either method is fine. It turns out that the second one is shorter when you have more variables, but either method's correct. So all we're really doing is we're breaking up the long right-hand sides with multiple shorter right-hand sides by introducing new variables. So we introduce the C1, C2, or the X1, X2. we're introducing new variables along the way. Any questions about that? Cool. Is this thing in CNF? Yeah, we can check. Well, there are no epsilon rules at all, so that's no problem. We have variable goes to one terminal everywhere, and all the other rules go to two variables, so it must be in CNF. Cool. But there's one thing that we should keep in mind throughout all of this. Throughout each of these 5 steps, did we have to do anything special or have to think about this grammar in particular in terms of what to do? Or could we apply this to any CFG at all? Yeah, any one. Well, the first one, we just tack on S0 goes to S at the top. We don't even look at the rest of the grammar. Eliminate epsilon rules. Well, we have that procedure of figuring out what the nullable variables are. And then what you do is you look at each of the rules and generate a whole bunch of extra ones if they have nullable variables in them. For the unit rules, we're just copying and pasting rules everywhere. The fourth one is you're just converting a terminal when it makes sense to its corresponding variable. And the fifth one is you're just making a chain of rules with new variables. So we don't have to think about the grammar in particular in terms of how to convert it to CNF. So this actually tells us something, that every CFG can be converted into CNF. Sweet. Yeah.
Is CFG the most generic type of grammar that we consider?
So it's the most generic one that we're going to work with, but it's not the most generic one in total. So there exist, so this is just purely for your knowledge. You don't have to learn about these. So there are these things called context-sensitive grammars, and beyond that are unrestricted grammars. So unrestricted, you can have anything on the left, anything on the right. Context-sensitive, you can have a little bit more than a variable on the left side and anything on the right side. So, and it turns out that some of those problems that you want to ask questions about for these two grammars are a lot harder than CFGs. And it turns out that context-sensitive grammars can recognize more than context-free grammars do. And proving things about them is a lot harder, so I'm not going to cover it. But yeah, there are things beyond context-free. Any other questions? Okay, so it'll turn out that CNF is extremely powerful, but we're not there yet. But it turns out that CNF is incredibly important for proving certain things about context-free languages. Okay, so when we were talking about regular languages, we had a machine model for them, DFAs and NFAs, and then eventually we got a grammar model, the regular grammar for the regular languages. Then we started talking about context-free languages, and we have a grammar model for them. So what thing do you think we're missing from context-free languages? So, yeah, a machine model. So we need a machine or a state-based model for context-free languages. So, well, we can't stick to DFAs and NFAs because context-free languages are more than the regular languages. So we can't just stick with DFAs or NFAs because they only recognize the regular languages, of course. So what can we add to the DFA or NFA model to have it recognize the context-free languages. What can we do to this model to have it recognize the context-free languages? So what kind of structure can we add to it? Well, I can't just say, well, you can have some data stored in these other states over here. So you have a set of states. In addition to the machine itself, you have these set of states where you can write additional info to. But that's not enough because the model can have any number of finite states. So if I allow those states to be included, well, then I just get regular languages again. So I need some kind of unrestricted resource of some kind. I can't just say, I'm going to restrict you to using so much memory or something, because I can incorporate that into the states if I wanted to. And I wouldn't be able to leave the regular languages. So we need to have some kind of unrestricted resource. So let's actually talk about that grammar that we had for balanced parentheses. So this is the grammar that we had, if I remember it right. I think that's right. No, it's not right. It's this, I think. Is this what we had before? I'm pretty sure it is. Okay. So if we want to generate a particular string, let's just say that we want left, left, right, right. So just a pretty simple string. What we would do is we would start with S, then we would get S, left, S, right, with S, and then what would we get? So I would make the first S disappear. Interesting. So I would make the first S disappear, and then let's just say we make the second S disappear. And then I'll expand the inner side of S, so then we'll get left, S, right, S, right. And then I'm not going to put every single rule here, but I'm going to make all three of those S's go to empty, so then eventually we'll get left, left, right, right. Okay. So let's see. We're talking about context-free grammars, right? So without loss of generality, well, is this a leftmost derivation? Am I processing the leftmost variable every single time? No, I'm not. Namely, this step right here, I didn't process the leftmost variable. But because we're talking about context-free grammars, could I have processed the leftmost one if I wanted to? Yeah. So let's think about that. So if I'm processing the leftmost variable, well, look at the terminal that I just generated right here, the left parenthesis. Is that ever going to change? No, because it's a context-free grammar. It'll never touch that terminal that I just made at the beginning. But when I get to a variable, of course, it might change. But the terminal that I generate on the left side will never change. And then when I make more terminals, they will never change too. So if we want a structure that is a state-based machine, we need to be able to process, and if we want to show that it's equivalent to a context-free grammar, we need to be able to process the string left to right like a normal machine, but we need a structure so that it processes the string exactly on one side. So if we're storing a derivation in some way, we need to access the derivation on one side only. So that tells me that we need a stack. Because, so what's a stack in computer science? Yeah.
The data structure that's first in, last out.
Yeah, so it's a structure where first in, last out, which means that you access only the things on the top of the stack. So how would this work here? So if we look at a stack representation of the derivation that we just did, so let's see. So then at the beginning, the derivation only has one thing in it because it only has the start variable. So on the stack, if we're storing this derivation on a stack, there's only one thing on there, which is the s. So what I want here is that at each step in the derivation, I want what we've derived so far to be on the stack. So in the next step, I want s left s, right s on the stack. So I'm not going to go into the details of how we do that yet, but at some point we're going to have, so this s is going to get removed because it's always replaced with the right-hand side of the rule. And so the stack contents will now look like this. So then, well, what is at the top of the stack now? After this second step? The variable s. We can always do a leftmost derivation, right? Yeah, we can always do a leftmost derivation. Where is the leftmost variable in the stack here that we are doing? On the top of the stack. Isn't that cool? That we can design the stack so that we're processing the leftmost variable first. So let's just say we process the leftmost variable. And, well, the rule says we're going to make it go away. We're going to make the s on the top turn into the empty string. So I'm going to remove it, and then the stack looks similar, but now a terminal's on the stack. So the terminal's on the stack. So can I replace a terminal with something? No, it'll never change. So what can we do here? A terminal on top of the stack means we can read it off of the input in the machine, because the machine is reading the input and determining whether or not it can be recognized, whether it's accepted. So here, if there's a terminal on the stack, we can read it off of the input. And if it's the wrong character, then it's not possible to be accepted by the machine. So I think this is actually pretty slick in that because we're doing a leftmost derivation, we can just put the leftmost thing on the stack. And because this terminal will never ever change, we can just take it off the stack and read it off of the input at the same time. So then when we get down to here, now again we have a variable on the stack, and it's the leftmost variable, which we can always work with. So here I would I'm not going to do the whole derivation here, but we're going to process this variable and apply a rule to it and change the contents of the stack in the process. And then we'll read more terminals off the stack if they're at the top, or if a variable's on the top, we apply another rule. because we're always doing a leftmost derivation. Isn't that cool? I think that's pretty slick. Any questions about at least the general idea? We're going to talk about the model in a sec. Okay, cool. So what are the things that we really need? So if we're going to make a machine model, well, what are the things in a machine model that we are all familiar with? So for a DFA or an NFA, what are the things we're allowed?
States.
Yeah, so states. What else do we need?
Transitions.
Yeah, transitions of some kind. Well, here it may change what the transitions are going to do, but we need transitions of some kind. What else should we have? Well, we need input alphabet for sure, because a DFA and NFA both have those. What else do we need?
Probably a start state.
Start state, yep. What about final states? Should we have those? Yeah. So notice something here. So there's one more thing that we're going to add. So the 5 basic things, we're going to add one more. So let's look at the stack here. So on the input, we're always going to expect a left parenthesis or a right parenthesis. Are we going to ever expect an S on the input? No, because that's not what the input alphabet has. So on the stack, we should be allowed to put whatever we want on the stack too. So yeah, so we're allowed to have a separate stack alphabet. So the input can have whatever characters it wants, and the stack alphabet can have whatever characters it wants too, because they're kind of independent of each other in terms of what can appear on either. So we have the 5 things plus the stack alphabet. So a push down automaton, the name of this is purely historical. They come from these things called push down stores, which is exactly what we're doing here, but it's just a different name for it. So a push down automaton, or a PDA. Now you can tell everyone you learned about PDAs today. This meant to be a joke. A push down automaton is a 6-tuple Q sigma gamma, so that's a new one, delta Q0F, where Q sigma Q0F are as in a DFA or NFA, it doesn't really matter. So then we have those 2 new guys. So gamma here is a finite stack alphabet. And then now we gotta, of course, talk about the most important one, which is the transition function. So let's see. So let's think back to what the NFA model was. So for the transition function for an NFA, so how did we design the transition function for an NFA? So we always, we picked a state, and what could appear on the transition for an NFA?
Just any symbol that's in the alphabet.
Any symbol or epsilon. So we had delta is a function from Q cross sigma union the empty union epsilon going to Well, with an NFA, could I go to a bunch of states if I wanted to? Yeah, I could. So, and we allow ourselves to go to any subset of the states. So how do I indicate that I can go to any subset of states that I want to? What is the collection of all subsets? The power set of the set of states. The power set of Q. Okay? So with a PDA now we have to incorporate the stack into account, right? So let's see. Well, what are the operations that you would normally have with a stack? Yeah, pop, so take something off. What else can we have? Push. Yeah, we gotta be able to push stuff on the stack, because if we can't, then well, there's no point in having a stack. Anything else that we need?
We might need to be able to shift, because like if we were gonna have, well actually no, never mind, because we're eating up the input. Never mind.
Okay.
I was gonna say maybe peak. I don't know.
Peak. Okay, so let's actually talk about peak. So what the ops that we can have are push, pop, and then maybe peak. Well, push and pop are completely necessary. You need to have those. Because if you just push stuff on the stack, then there's no point in really having a stack in the first place. And pop is the same thing. So what about peak? Do we really need peak in order to carry out something here? Or can I accomplish peak with the other two operations? I think I can. So what can I do? Well, I can say, if you can pop this character, then I'll push it back on. So in order to peak, say, an A on the stack, I would just say, if you can pop an A right now, then I'll push it back on. So that would allow us to, quote unquote, peak that there's an A on the top. Well, what if there was a B on top? I could have another transition that says, if you can pop a B, then we'll push the B back on. So then, in effect, we can actually figure out what character's on top of the stack. So it turns out that we don't need peak here. We could include it if we wanted to, but we can accomplish it with the other operations. Any other suggestions? Yeah.
Check if empty.
Check if empty. We will find a way to mitigate that. And one thing that we should note here. So if I push into a stack, would that ever cause the stack to be empty? No, so we'll allow ourselves to keep pushing into a stack as much as we want to. So the stack can grow as big as we want. The pop operation, well, that might cause problems. So if the stack is empty, then if we tried popping it, then what we're going to do is the computation will stop if we pop an empty stack. Yeah, I think we have time. Okay. Yeah.
Can you make clear operation?
What is clear?
Like the empty?
Yeah. Actually, that's another good point. So what was the notion of acceptance in a DFA or an NFA? How did we say that we accepted back then?
It was that we finished reading the input and we were in the final state.
Yeah, so we finished reading the whole input and we were in a final state. That's going to be exactly the same criteria here. So to accept a string, we have to read it all and be in a final state. But that tells us that if we're in a final state and we've read everything, it doesn't matter what is on the stack. And that's the case here. So we can have anything that we want on the stack when we finish. So I don't think we would need a clear operation, but it'll be actually convenient that we, in some sense, clear things, because what we can do with a PDA is in a final state, if there's nothing coming out of the final state, we can just have self loops on it that just pop everything else off. And it doesn't have to take that transition, but it could if it wanted to. So it'll make more sense as we do this. But we don't need a clear operation. So when we accept the stack can have any contents when it accepts. Okay, so what do we need for the transition function then? So, and also, this is actually kind of important. Which of the two operations should I do first? Should I be able to push first, or should I pop first?
I feel like you should push first so we can get our start state.
So suppose that we wanted to push an A and pop a B. So if I push an A on, and then I try to pop the B, well, what's on the top of the stack now? It's the A that we just pushed. So which of the two operations do we have to do first? We have to do the pop first. So we have to pop first and then push. And we shouldn't be allowed to pop if the thing on the top of the stack is different than what we're saying to pop. So if the top is an A and some transition says, I want to pop a B, I can't execute that transition because the stack contents are different. So what we should have in the transition function is we should be able to be in a state, cross. Well, here we're going to proceed like with the NFA, where we can either read a character or not. So it's exactly the same. But in addition, we should be allowed to pop, because that's the first operation we have to do. We should be allowed to pop or not. So here, we're going to have another cross with gamma union empty. So that's the left side of the transition function. And then the right side is, I should note here. So this part right here that we just added is for pop, the pop operation. And then we're going to have one for the push. Well, we should be allowed to have a transition that goes to another state and pushes, let's say, an A, and then another similar transition that pushes a B. So we should be able to go to a state as well as have multiple transitions that one pushes something, another one pushes something else, another one pushes something else. So we should be allowed to go to any one of those combinations. So here, we're going to have the power set of, brace yourselves, Q cross gamma union epsilon. And this part that we added inside the power set is for pushing. People outside looking at this going like, what in the world are they learning in there? Yeah. So when we're going to actually do PDAs next time, this will be far easier than it looks. It just, we have to provide the definition of the transition function formally, but once we start making PDAs, it's going to be way easier. So I'll see you on Friday.